All right, 8.2, area between curves. So the integral from a to b of f of x dx produces a value of the signed area, so area under the curve. Now, the signed area can be positive, negative, or zero. But when we talk about actual area, it can be negative, right? You would never say that square is a -4 area. So let's keep that in mind. And other times that we do this, what we might do is have restrictions. So that way we have that positive area. So we're going to talk about the area of a region between two curves. And so right here we have our f of x. Right here we have our g of x. So the area of the region between the two curves is actually the integral from a to b of f of x minus g of x. So f of x being on top, that maximum almost, to that g of x on the bottom. Well, this f of x minus g of x, you can think of as your height of that shaded area. And the d of x, or dx, is like our width. Now, a couple of things need to happen here is f and g have to be continuous. And of course, because we have this order of f of x minus g of x, f of x must be greater than or equal to on that interval. Otherwise, it changes. And you'll see as we do some examples down below what I mean by that. Now, let's also talk about what functions we have, because usually, most of the time, right, the functions we deal with are functions of x. So when we think of the x-axis, right, we have to think of that height being top to bottom. But when we do functions of y, which is our vertical here, we have to think of, max to min, which means right to left, because our right values are greater than our left values. So let's keep that in mind, especially when it says functions of y, because that's kind of new. All right, so example 1. Find the area of the region bounded by y equals x squared plus 2, y equals x equals 0, and x equals 1. Okay, so this graph here is all of these functions. So there's our x squared function, our x, and our vertical 0 to 1. This allows us to tell us that we're going from the x value of 0 to 1. So let's set up our integral. And our lower boundary is going to be 0. Upper boundary is going to be 1. Now, when you think of f of x minus g of x, it means our top minus our lower. What function's on the top? Well, it's x squared plus 2. Now, I'm going to put this in parentheses right now for future things. You'll see why in a minute, because I'm going to subtract the bottom, which the bottom function is x. Now, a bunch of you might say, Ms. Heckman, why did you put x in parentheses? Because it doesn't have to be. The reason why is because I want to get you in the habit, since this function, this lower function, doesn't have to be just a monomial. It could be a bunch of terms. And if it is, since we're subtracting the whole function, you want to subtract every part of that function. Okay. All right, here we go. So if we were to rewrite this, so we're like, we can get rid of these parentheses. I would have x squared plus 2 minus x, and then the x, and what do you know, when we take the integral here, it's just the power rule. So we get x cubed over 3 plus 2x minus x squared over 2. And we're going from 0 to 1. All right, so we put in our max first. So 1/3 plus 2 minus 1/2. And then minus our lower, right? Well, all of our lower stuff is when we put in our zeros, we get 0. If we talk about fractions and we add and subtract, meaning we have common denominators, this comes out to be 11/6. Very good. Okay, sometimes you have to find where two curves intersect to determine the boundary. So right here, we know the boundaries are 0 and 1 because that was given to us. But sometimes our boundaries aren't given. So how do we do that? We have to find where they intersect. Now, you must show an equation setup, even if you are using your calculator, okay? So you need to make sure you do you write down what you're setting it equal to, and then your answer. So one thing I want to point out with example 2 also is we are in terms of y, a function of y. So a couple of things to keep in mind. We're thinking about right to left, and we want to, even though we can graph this, when we solve for intersections, we need to make sure that we solve for x. So this would be x equals y minus 1. Okay, so that helps us solve for it. But let me graph this in general so we can see what the graph looks like. This is linear. So y intercepts at 1. We go up 1 over 1. Up 1 over 1. Or down 1. I'm going down. There we go. So this is our linear. Now, think of this. This is our parabola, but we're going towards the right there. So which this means is instead of this being our y-intercept, it's going to be our x-intercept. Okay. Now, I know it's a parabola, but I got to figure out where it might connect. So what I'm going to do, instead of graphing this right away, I'm going to find out where they intersect. So I'm going to set this equation equal y squared minus 3 equals y minus 1. I'm going to do this algebraically quick for you, but if you're able to use a calculator, make sure you just type them into y1 and y2 and find where they intersect. I know many of you are saying, Heckman, how can I put this in a calculator when we're in terms of y? You can make it in terms of x's and then just switch the values, just to tell you. But let's just solve it algebraically. So I'm going to move everything to one side. Y squared minus y minus 2 equals 0. I'm going to factor. So y minus 2 times y plus 1 equals 0, which means y equals 2 and y equals negative 1. So they intersect when y equals 2. And look, we have that. So they're intersect there. So I'm going to curve that. And they intersect when y equals negative 1. So they intersect right here. And of course, these guys continue, but we only care about the area in between these two functions. So all of that right there. So our boundaries, because we're in the function of y, are our y values where they intersect. So our lower boundary where they intersect is y equals negative 1 and y equals 2. Okay, now remember, because we're in terms of y, these are the y values. Then we take our function all the way right to all the way left. So if I look, what function is on the right side? The linear function. So I have, and of course, since I'm in terms of y, guys, I have to use that one. So y minus 1 minus our function that's to the left, which is y squared minus 3. See why I put those parentheses in there? And then, of course, this is dy. Okay, let me simplify this and then take our integral. So -1 to 2 y. Let's see, this is going to be -1 here, but this here is going to be +3. -1 and +3 is a +2 minus y squared dy. Take our integral, we get y squared over 2 plus 2 over 2y, not 2 over, minus a y cubed over 3. We're going from -1 to 2. All right, so I'm going to squeeze it in here, guys. So I'm going to put my upper boundary in first. So 2 squared is 4, so I get 4 over 2 plus 2 times 2 is 4 minus 2 cubed is 8 over 3. Now let's keep in mind that when we subtract the lower, this needs to be in parentheses because we're subtracting all of it. So -1 squared is 1, leaving us 1/2 here. 2 times -1 is -2. -1 cubed is -1. So minus the -1 would be plus. That's 1/3. So plus 1/3. Now, when you do all your fractions and you get that all together, you find that you are at 9/2. Sorry, maybe I wrote too big that I didn't have enough space. Okay, our last example, be careful. I want to show you this. First of all, I can see that we're in terms of x's and our functions are good. Now it says set up the integrals for the total area of the regions locating between two curves as shown. You may use your calculator. So remember, when you use your calculator, you actually have to show what you're putting in for your intersections, okay? So how do we find our intersections? We find our intersections by taking one curve and setting it to the other. Now, of course, this means in your calculator right now, and I had somebody borrow my calculator, so I need you to trust me. This one is going to be y1. That one's going to be y2. And find your intersection on your graph. If you want, pause the video right now and you can figure it out yourself and see if you're right. Otherwise, you find that x equals, and we always got to go out 3 decimal places, -2.25. We have 0 and 2.025. Now, some of you might be saying, wait a second, we have 3 intersections. What does that mean we have to do? Well, what I'm going to do is add some color to this so you guys can see what is happening. So this right here is our f of x, right, in red. Do you see what's happening? We actually have to make 2 integrals because in this first half right here, our f of x is above the g of x. So for this half here, we're going to say f of x minus g of x. But if we look at it over here, our g of x is actually on the top and our f of x is on the bottom. So we have to create 2 integrals to be able to solve for this. So our first one here, remember, this intersects at the -2.025. So we're going to go -2.025 to where they intersect here again at 0. And in this case, we are going to do our f of x minus our g of x. And then to find the total area, though, because everything's going to be positive, remember, with total area, we're going to add on the second part. The second part, our lower boundary is at 0, and we go to our upper boundary where they intersect at 2.025. And our upper function is g of x minus f of x. Forgot to put the dx in there, guys. Very good. Now, some of you might be saying, heck, been saying my name a lot today, huh? Why didn't you just put in the functions? Well, we can use our calculator. And if you already put this for y1 and this function for y2, we can just use our calculators to give us the integral of each piece. Okay. Okay, it looks like I do need my calculator, which I don't have it right now, so I should borrow one of my own. I already put in y1 that first function, that f of x, that second function in y2. So now I'm going to go back to my original screen. There we go. I'm going to go math, integral, and I'm going from the negative 2.025 to 0 of y1 minus y2 dx. Okay. And I'm going to add that on to the integral from 0 to 2.025 of, we're going backwards right now, right? We're going y2 minus y1, also dx. And we enter, and there is our value. So our area is 8.405. Awesome. Now try some practice.